So I'll start, right? Okay. Okay. So this is the last go at this, and today I'll start off talking about gravitational instantons. These are solutions to Einstein equations in dimension 4, which are either defined on compact four manifolds or on non-compact four manifolds, but they are complete, geodesically complete, and such that the, well, some different ways to phrase it, but I'm going to say such that the total integral of squared Riemann curvature is finite. So these are solutions to Einstein equations, and this could be with or without cosmological constant in dimension 4, which are Riemannian. And either compact or complete, and I mean I'll be more precise about this, but you want these solutions to asymptotically look like in inverted commas for now a flat space. Condition one of an as is that the integral over the four manifold M of the metric norm squared of the Riemann curvature is finite. See what this condition does, it tells you that the curvature of these solutions is localized in a finite region, and that is what a concept of instanton is. I mean, instanton. If you look at these solutions, and sometimes you can, I'll give you an example, as analytic continuations of Lorentzian solutions, then you want them to be localized in the Euclidean instant of time. Okay. Now, the compact situation is very interesting, but somewhat formidable. Okay. So you'll find that in the compact, simply connected case, M either has to be a flat torus or M as a manifold, it's what's called the K-free surface, which is known to carry a Ricci flat. I mean, let me actually, to be concrete, let me assume that these Einstein's equations have lambda equal to 0. So this K-free surface is complex to surface of a four manifold. It carries a Ricci flat Kähler metric, but it can be shown that this metric doesn't admit any continuous isometry, so it's a kind of hopeless task, but still an open problem to find it explicitly. Well, I'll focus on the non-compact case. But we'll return to this K3 at one point. And let's, to relate this to other lectures of this school, which I sadly did not attend, or I think I wanted to relate it to those. I want to give you an example, lots of examples today, and look at the Euclidean Schwarzschild solution. Okay, so that well, we take the Schwarzschild metric describing a black hole, and we're going to write it down in the kind of standard elementary first year GR course coordinates, not the Eddington coordinates. But we're going to replace the t, the time in this metric, by I times tau, and that way we turn it into a Riemannian metric. So it is G is 1 minus 2m over r d tau squared plus 1 minus 2m over r inverse dr squared plus r squared d omega squared, where this omega, d omega squared is a metric on a round two-sphere. Now, you know that the Lorentzian Schwarzschild metric has, the way you write it, two types of problems. There is a problem at r, apparent problem at r equals 2m, and that is the, well, we now understand, it took decades to sort that out, but we now understand that this is not a real singularity, but a coordinate singularity. It's a location of a black hole horizon, and you can go beyond it by changing to a better coordinate system. But this other problem at r equals 0 is a serious one, and you're not going to avoid that. In this case, I'll claim that this metric is actually a regular solution to Einstein's equations. I claim it's obvious at this stage that this metric is Ricci flat, because all we've done, you see, is we replaced t by I tau, and the computation of the Ricci tensor does not depend on this, right? So your an analytic continuation of a Ricci flat metric is Ricci flat. But how the serious problem is the singularities. So I'm going to make it regular. I'm going to restrict the range of R, allow range of R to be 2m to infinity. Now, so it'll never be 0, because the smallest it gets is 2m. But well, I can't really just say it here, because if r equals 2m, this term blows up, and also what stops him from going through this r equals 2m? How do I know that it's geodesically complete? Well, let's kind of analyze it locally. So let's zoom near r equals 2m, and the way we do that is we'll introduce another coordinate. Okay, so we replace r by a coordinate rho, and I'm taking rho to be 4m. We'll do this computation in real time. 4m, a square root of 1 minus 2m over r, and we're going to expand this metric around. See, r equals 2m corresponds to rho equals 0. So we're going to expand it around rho equals 0. Okay, so we'll do that. Well, this term is easy to deal with. This will be just 16m squared d omega squared. This term is easy to deal with, because we just need to square this and divide by 4m, or 16m squared. We'll come back to this. This term is a bit of a pain. So compute, so I get rho squared is 4m, in fact it's 16m squared, 1 minus 2m over r. So if I differentiate it, I get 2 rho d rho equals 32 m cubed over r squared. I can divide by 2, so I get rho d rho equals 16 m cubed over r squared dr. So this really will be near r equals 2m. This is r squared is 4m squared. It'll be just 4m dr. Okay, so I'm interested in, now I compute this. So what's g? See, let me start with this term. So this term is rho squared over, no, in fact it's the inverse. It's 16m squared over rho squared, you see, because I need 1 over this, times dr squared, but dr squared is rho squared over 16m squared d rho squared. So it's looking good. Well, I'm only in that something has become regular, d rho squared. Then I have this term. Well, this term is easy. I divide by 4m and square it. So I have plus rho squared divided by 16m squared d tau squared plus 4m squared d omega squared. Okay, now this is 1. So, yeah, so this is really, just d rho squared. And if you're familiar with writing a plane metric, dx squared plus dy squared in terms of plane polars, then you see that we can package this term together into a metric on R2, and the apparent singularity at rho equals 0 is just a singularity of the radial coordinate system. But for that, this coordinate tau must be periodic. It's like the phi in the plane polars with the fine-tuned period. So what does the period of it has to be? So this is regular. If tau over 4m is periodic with period 2 pi, so tau has to be periodic with period 8 pi m. Okay. And if this is the case, then you obtain a regular metric, and this metric is defined on R2 cross S2, and asymptotically, that is, as rho tends to infinity, see what happens, we have to go back here, and asymptotically, this just tends to a metric on a circle, and this tends to a metric on a sphere with radius infinity. So asymptotically, this metric is, for fixed R, is a metric on S1 cross S2. So this is asymptotic to S1 cross S2. One says that this is what's called asymptotically flat, or AF. There is an interesting story here to, if you think really in terms of the Lorentzian Schwarzschild, because these factors of 1 over 4m, which enter the periodicity, that should remind you of the surface gravity of the Schwarzschild black hole. And in fact, this sort of approach initiated by Stephen Hawking and gave a fairly simplified derivation of the black hole radiation, where you've sort of argued that the temperature of the Hawking temperature is inverse proportional to the period of this coordinate tau. And this was really a huge simplification comparing to the Bogolyubov transformation computations. But that's not what we'll be concerned about. We'll go with examples like that. So this is asymptotically flat. You see, there are other instantons I'll tell you about, and they'll be asymptotically locally flat. What does that mean? Well, that means that at infinity, rather than a metric being asymptotic to a product metric on S1 cross S2, you have some S1 bundle over S2, but not necessarily trivial. See, this is a trivial S1 bundle over S2. You can have other ones. Okay, in terms of informally, the way you tell the difference between this and that is that in the Schwarzschild case, this d tau square term is alone. You don't have any kind of connection on this line bundle, which would be a circle bundle, which would be d tau plus some one form squared. So that will be one class of instantons, gravitational instantons. There are also other classes, and one of the prominent ones is called ALE. These are called asymptotically locally Euclidean. And they also satisfy this instanton definition, except that asymptotically they look like R4 quotient by some discrete group gamma, and this gamma is taken to be a discrete subgroup of SO4. Okay, the sort of the names you might have heard of some particular examples of these instantons. Well, this one contains self-dual Taub-Nath, and this one contains Eguchi-Hansen. There is, you can ask, well, given that amongst these asymptotically locally flat examples, there is a real asymptotically flat example, which is non-flat, Schwarzschild, you might ask, are there solutions which are really asymptotically Euclidean rather than asymptotically locally Euclidean? And the answer to that is no. There is something called the positive action theorem, which tells you that, well, that if a metric is asymptotically Euclidean, it has to actually be Euclidean. Right, so let's venture into a territory where we'll have some of those more complicated examples. So my second class of examples will be really a class of examples known as the Gibbons-Hocking Ansatz. Okay. Well, the setup here is this. We'll take a function on R3 and we'll take a one form on R3. So we take some one form A, which is AI dxi, and the components of this one form depend on x. Okay, and in terms of this function and the one form, we'll write down the following expression for a metric. So G is V times dx1 squared plus dx2 squared plus dx3 squared plus V inverse times some d tau plus a squared. Going to be the number that will be 4.1. And this is, so x1, x2, and x3 are coordinates on R3. Now, Well, we will want this metric to be Ricci flat, and in fact, the kind of form of V and I I'm going to give you will be also such that this metric has anti-self-dual Wall tensor. So remember, we finished the last lecture by generalizing following Penrose's Twistor theory to a curved space-time setup, but that came at the price of restricting to only metrics which are conformly anti-self-dual. So it'll be one of those. So in an exercise for you, (4.1) is anti-self-dual in terms of the Wall tensor is anti-self-dual and Ricci flat. Well, we expect some conditions on A and V, and this condition boils down to a linear equation, which is that dV star, and this is a hot star of the three-dimensional metric, that equals dA. If you want to, you can write this into elementary vector notations. Equivalently, you can say that the gradient of V is the same as the curl of A, identifying vectors and one forms on R3. Okay, so this in particular, by taking a differential of this equation, that tells you that V has to be a harmonic function on R3. Now, it'd be good for you to do this exercise, but I'm going to give you, and really do it by computing all the tensor components and all that, but I'm going to give you a streamlined proof, like an alternative method, which will teach us something else. An approach to this exercise. But because I'm taking this approach, you're not allowed to take it. You have to take the direct approach. So the approach is this. If Ricci tensor is 0, so Ricci tensor dies, all there is left to the curvature is the Wall tensor. Now, the Wall tensor, we want to be anti-self-dual. Well, that means that in the Ricci flat case, the Riemann tensor is actually anti-self-dual. This actually is equivalent. These two are equivalent. Well, what that means is and now I'm going back to these three isomorphisms I told you about. This means that the curvature vanishes on alpha surfaces, or alternatively, that the connection, the Levi-Civita connection, is a flat connection on the bundle of self-dual two forms. Now, that means that there exists a flat, the connection induced by the Levi-Civita connection on the self-dual two forms is flat. Well, that means that we can pick a basis of this space. So it's a three-dimensional, the fibers are three-dimensional. We can pick a basis, so three self-dual two forms, which are covariantly constant. So it's still. Well, let's call this basis omega 1, omega 2, and omega 3. We can actually, if we have a flat connection, we can choose it we can choose a spin frame, a frame on this bundle I called S prime, so that the components of the connections vanishes and these two forms are actually closed. And one often does that. Now, given these two forms, I'm going to define three endomorphisms. So define three endomorphisms. I'm going to call them capital II on Tm by saying that g of x I y is omega I. I'm taking this, I can choose them to be non-degenerate, well, of x and y, and that has to be true for any vectors, any vector fields x and y. See, then this, so essentially what I'm doing is I'm raising an index on omega using g. That gives me endomorphisms. Then you'll find that this endomorphisms satisfy the algebra of quaternions, and they parallel, so I1 squared equals I2 squared equals I3 squared equals minus identity, together with your favorite I1, I2 equals I3 equals minus I2, I1, etc. And that turns this, well, what we've just kind of proved, it's a sketch of a proof, but we've proved that anti-self-dual Ricci flat is what pure mathematicians called hyperkähler manifold. So a hyperkähler manifold is a manifold equipped with such three endomorphisms which are compatible with the metric, they're Hermitian, and they're covariantly constant. Now, this is general consideration. It goes beyond this Gibbons-Hawking ansatz. So what's special about the Gibbons-Hawking ansatz? Well, if there exists a Killing vector k such that a Lie derivative along k of all these free forms is 0, such Killing vectors are called triholomorphic because they preserve free complex structures. If that happens, then you can show, and that was shown by Nigel Hitchen first time, that the metric has to belong to this Gibbons-Hawking class. And the way you do that is you kind of need to adopt coordinates to it in a geometric way, and this goes via moment maps. So, I mean, maybe the term Hamiltonian is more familiar to you. So, you see, you can take any of these two forms. It's Lie derived by k, therefore k is a Hamiltonian vector field for this two form. It must have some Hamiltonian. But there are three of the two forms, so there are three Hamiltonians, call them x1, x2, x3. These are the coordinates, and once you have these coordinates, you can kind of do the rest fairly algebraically. And that will take you to 4.1. Now, why will it simplify my exercise? Well, because I can then go back to 4.1 and write these two forms explicitly. And what are they? So I think they'll be, can I do it without deriving it? I'm going to just stare at this. Okay, so the one no-brainer term is dxi wedge d tau plus a, and the other term therefore must be good. It'll be epsilon ijk dxj wedge dxk. Okay, and once you do that, you just have to check that these two forms are closed. And the closure of these two forms gives you the monopole equation. By the way, this one is called the abelian monopole. Okay. Well, so far, these are kind of local considerations in that we're not guaranteed to have any instantons. We have solutions to anti-self-dual Ricci flat equations. So for instantons, we must pick some better V's, or V's which will give rise to regular metrics. And what one does is one picks n points on R3 with position vector x1 up to xn. In the UK, they write vectors underlined, not with arrows. Okay, and you pick these points, and then you take v to be some constant v0 plus a sum from m equals 1 to n of some constant cm divided by mod x minus xm.
I have a question.
Yes.
Because you have this equation that Hodge star of dv is equal dA.
Yep.
So to have 0 of d omega a, you should probably have v in this formula. But you don't.
Yes, I do. Don't I?
Yes.
Thank you. Good. Because mentally I had it. I really had it when I was deriving this. The v is here. What happens is you take the sort of orthonormal frame and you take wedge products of things in this frame. And now you really see that it can work, because if I did this, I have a bit of dv, but then I have a dual of this. Right, so I take this v, so this multi-centered metric, they called. And they'll be containing this ALE, not all, but some ALE and ALF instantons, right? So how do you distinguish between the two? If you take V0 equals 1, or a constant, but non-zero constant, we can normalize it to 1, we'll get a subclass of ALF metrics. And the most prominent of those is if we take V, so e.g., V is 1 plus some constant m. M is a bad index. Call this k. I apologize. Plus some constant m over r. You think that this might be singular at r equals 0, but at the level of the metric it isn't, by the sort of calculation I gave you for Schwarzschild. This is called the anti-self dual Taub-Naht. Another alternative, so it turns out that the case where V0 is a zero constant or a non-zero constant differs dramatically at the level of the asymptotics. If you take V0 equals 0, then you have a class of ALE metrics, and the best known of this, they called AK ALE metrics. They correspond in ALE definition. I told you need to divide by some discrete subgroup of R4. In this case, you get the cyclic subgroup. If you take m equals 2, so you just have a superposition of two fundamental solutions. Well, you can choose the origin so that x1 and x2 are negatives of each other. That one gives you the Eguchi-Hansen metric, or it is the Eguchi-Hansen metric. See, back in late 70s, early 80s, where these things were first thought of, only these three instantons were known, the Euclidean Schwarzschild and these two, but now we know many more. See, the difference between this Gibbons-Hawking ansatz and class and the Euclidean Schwarzschild is that, unlike the Euclidean Schwarzschild, these do not arise by an analytic continuation of any Lorentzian metric. So they have no Lorentzian counterpart. Why don't they? Well, because they have anti-self dual Wald tensor, and I've told you that you cannot have that in Lorentzian signature. And yet they, in Euclidean quantum gravity, they contribute to path integral. I mean, I'm not, I don't come from a school of Euclidean quantum gravity, but to be fair to this theory, it's a very robust thing, which is here to stay. I mean, when it was first conceived by Hawking, it was probably regarded by him and others as a candidate for a fundamental theory of quantum gravity. Nobody believes that anymore, but it is the case, I think, that if, whatever quantum gravity is, if there is a limit at which quantum gravity approaches classical gravity, so in analogy to quantum mechanics, you would call it the quasi-classical limit, then at the kind of quasi-classical instant on approximation, this theory of gravity must be Euclidean quantum gravity where instances contribute to the action. So there is really some physics behind that. So I made a comment which sidetracked me. Good, fine, okay. So this Gibbons-Hawking ansatz, they don't exhaust all gravitational instantons, and they don't exhaust all anti-self-dual Ricci-flat solutions. But there is another simple formulation which involves an equation which at least locally gives them all. So this was a breakthrough made by a Polish physicist Jerzy Plebański, who has shown that locally there exists a coordinate system called these coordinates W, Z, W tilde, Z tilde. I mean, for a reason, I'm using the same notation as I've used in my complexified Minkowski space, such that all complexified anti-self-dual Ricci flat metrics take a form which is this. So G is omega. Omega will be some function I'm just about to elaborate on. Omega W, W tilde, dW, dW tilde, plus omega W, Z tilde, dW, dZ tilde, plus omega Z, W tilde, dZ, dW tilde, plus omega Z, Z tilde, dZ, dZ tilde, where omega is a function of these coordinates, and it satisfies a single nonlinear PDE. And this PDE is this: omega W Z tilde, omega Z W tilde minus omega Z Z tilde, omega W W tilde equals 1. That's so and my notation is so that omega W means the same as d omega by dW. This is called the call it 4.2. It's called the first heavenly equation, and it's a good story why it's called that, but I'm skip it for now. Okay, and it's a nonlinear equation of a Monge-Ampère type, and it's equations where nonlinearities are in the highest order of derivatives. They're really hard to crack, both in terms of explicit solutions and geometric analysis. But a solution we can just write down is this. We can take omega to be Z tilde minus W tilde. And if I do that, if there is justice, and there appears to be, then because it really does satisfy this equation with these signs, this corresponds to the flat metric, which I wrote down in complexified Minkowski context. Now there are reality. So this is complexified. You can say what are the reality conditions which will guarantee that this metric is actually a Riemannian metric. So Euclidean reality condition we'll take z equals z tilde, w equals minus w, sorry, z, I wanted this, z tilde equals z bar, w tilde equals minus w bar, and omega real. Okay. So this omega in this hyperkähler story I told you about here, this omega is what's called the Kähler potential. It's a Kähler potential for one of these Kähler forms I've used. Now, I shall briefly comment on, I mean, my story really is about non-compact instantons, about the compact ones. So around that time, a couple of years later, this equation was analyzed in the context of trying to find, trying to show that the hyperkähler metric exists on this compact surface K3, and what was needed then. You see, Kähler potential is not something to which is I mean, it's a local concept. But if you fix a Kähler form, then a neighboring Kähler form will differ from it by d bar of some Kähler potential, and that's a global concept. And what was necessary was a proof of existence and, to some extent, uniqueness of solutions to these equations in this compact case. And that was, this existence was known as the Calabi conjecture. Now it's a theorem. It's proved by Yau, and that proof really contributed to his Fields medal that global solutions exist on these compact manifolds. But we'll be studying the non-compact examples. Okay, now I now want to go back and relate this to Twistor theory. So go back to Twistor theory, and I'll sketch how very concretely you can go directly from this Plebinsky formulation and this first heavenly equation to construct a Twistor space, and conversely, how you can deduce it from the Twistor space. So this is, something I did together with Lionel Mason, so 2 decades ago, really. Let me write down one formula and now I stop. And this formula is an observation, then I stopped before the break, is the observation that this first heavenly equation, which is 4.2, admits what's called the Lax pair. So what does that mean? I'm going to write down 2 vector fields. L is omega w tilde d z tilde minus omega w z tilde d w tilde minus lambda d by d omega, where lambda is some parameter, and m is omega z w tilde d z tilde minus omega z tilde d w tilde plus lambda dz. And one observation, which will prove to be profound, is that if equation 4.2 is equivalent to the Frobenius condition that the Lie bracket of these vectors L and M is 0 for any parameter lambda. That's what's known in the integrable systems literature. That's known as the Lax pair. So we have a nonlinear equation as a compatibility conditions for these 2 linear operators to admit the same kernel. And that's where I stop, and I propose we meet in 10 minutes or 12. Cool. Right. So the observation is that the commutativity of these two vector fields, where lambda is now an unmodified parameter, is equivalent to this first heavenly equation, and therefore to the anti-self duality and Ricci flatness of the metric 4.2. Now, what's going on? So the role of lambda. So because the metric is, if the equation holds, the metric is, if the equation holds, all these operators commute, the metric admits a three-parameter family of alpha surfaces because it's anti-self-dual. Now, you can fix a point, right? So remember, a point in space-time corresponds to a CP1 in the Twistor space. So if you fix a point in M, then there is a whole CP1 worth of alpha surfaces through this point, and this CP1 is parametrized. I'm choosing, I'm not covering the whole of CP1. I would have to do it at one more point using a different coordinate to cover the whole CP1, but lambda or CP1 labels the alpha surfaces through each point. So this lambda really is an affine coordinate in CP1. So where these operators, the vector fields, really live is not M. Now I've called one of these operators M. That was a mistake. I mean, it wasn't a mistake, but it was, given that I'm using M for the manifold. So I'm going to call this L0, and I'm going to call this L1. I apologize. And that's L0, and that's L1. Okay, so I'm going to construct what's called a double fibration. Yes? No? Okay. Double fibration picture. Okay, so there is this M, and I can construct a space, a point of which consists of a point in M together with an alpha surface through this point. And there is a CP1 worth of those. So this space I'm constructing is M cross CP1. And it fibers over M. Sometimes it's called the correspondence space. You're using the three remarkable isomorphisms, you can, and in fact it's transparent, you can convince yourself that this five-dimensional space is a projectivization of this primed spin bundle, right? So remember, S prime was a rank 2 bundle over M, so it was a six complex dimensional. Its projectivization fiber-wise is 5 complex dimensional. But to be concrete, I'll just stick to this picture. I can then take a quotient, or aim to take a quotient of this 5-dimensional space, look at the space of leaves by this integrable distribution spanned by L0 and L1. And that'll give me something 3-dimensional, and the result is that what you get is precisely this Twistor space, which then ticks all the boxes in Penrose's nonlinear graviton theorem, right? So this is, 4-dimensional, 5-dimensional, 5 minus 2 equals 3. Now, but the real, the this part is sort of, well, you have to do some calculation to make it all precise, but it's to be expected and somewhat straightforward. The interesting part is how do you go back? So if you just have a Twistor space and there are no chosen coordinates parameterizations, how do you recover an anti-self-dual metric together with this preferred parameterization? .1 and 4.2. See, so let's start with a Twistor space, and it's a Twistor space of a Ricci flat anti-self-dual for manifold, and so it has it fibers over P1. I think I called this fibration mu, and the sections of these fibrations are rational curves, they copies of CP1 with this prescribed normal bundle O1 plus O1, and there is a 4-parameter family of those, and this 4-parameter is going to be the spacetime. Now, to do this concretely, let's parameterize these rational curves. How can we do that? Well, let's pick 2 points on CP1. One of them will, so lambda is the coordinate on this CP1. One of them will be at lambda equals 0. And one of them, well, I should really be working in homogeneous coordinates, but I'm going to abbreviate it by saying lambda equals infinity. So what I really mean is I have a covering of CP1 with these homogeneous coordinates pi 0 prime and pi 1 prime, and I'm choosing pi 0 prime equals 0 here and pi 1 prime equals 0 here. But by the way, this, I mean, coming back to this picture for a moment, see, this picture kind of tells you what it is you would want to call a Twistor function. So any function on this space which is constant along L0 and L1 descends down to the Twistor space. It's a Twistor function, and 1 forms descend down to the Twistor space by Twistor 1 forms, and so on. But now I'm forgetting that I have these, I just have that. And I've picked these 2 fibers. And these fibers are just copies of C2. Now, I can pick one of these Twistor curves, and there is a 4-parameter family of those, and I can parameterize this curve by its intersections with the fibers. Here's a curve. And it'll intersect this fiber, and it'll intersect that fiber. And I can choose coordinates on these fibers so that this intersection corresponds to 2 complex numbers. The fibers are just copies of C2. This I can call W and Z, and this I can call W tilde and Z tilde. And because there is a 4-parameter family of these curves, the 2 intersection points with the fibers specifies a curve uniquely. And then what you do is you try to construct, you see there are 2 ways to construct a curve starting from a point if it belongs to a 4-parameter family. Either you specify 2 points, so it's like a boundary value problem for the curve, and you solve a Hamiltonian system of ODEs for this curve on the Twistor space. And that will ultimately lead, as I'll show you, to this first heavenly equation. Or you can specify a point in the direction of a curve, and that ends up corresponding to yet another discovery of Plebański, which I like even better than this, called second heavenly equation. But time is finite, so I'll just talk about one. So I've chosen this parameterization, and then see what happens with respect to this parameterization. If I concretely think of these Twistor coordinates as omega 0, omega 1, pi 0 prime, pi 1 prime, with pi 0 prime divided by pi 1 prime equals lambda. So in the flat case, this omega 0 and omega 1 were just linear functions of lambda, and the coordinates there were the parameters of the curve. What happens here is you can argue, and to do that you need to use the fact that these fibers are symplectic, that you can expand omega 0 and omega 1 in the Laurent series around lambda equals 0, and to the first order omega 0 is w, because that's how we've defined w, and to the second order it ends up being a derivative of some function omega which doesn't depend on lambda, so it's a function on m, with respect to z, and there are some higher order terms, and then omega 1 is z minus lambda d omega by dw plus some higher order terms. Now, so the point here is that you deduce this existence of this omega, and you do it by analyzing this O2 valued symplectic form, which is d omega 0 wedge d omega 1 at constant lambda. Okay, and you then need to build the higher terms in this Laurent series, and this is done by a recursive procedure. So what turns out is that all these terms satisfy a wave equation, a background couple wave equation on M, and you end up constructing this uniquely, but you also discover, and for that you go back to this double vibration picture. I call this vibration mu, let me call this S. I didn't use S. You discover that if you pull back, if you call this form sigma, and you pull it back to the correspondence space, you see on the Twistor space, this is a two-form on the two-dimensional fiber, so sigma square equals 0 identically, but on this space, which is 5-dimensional, this gives you a condition, so pullback of sigma, wedge pullback of sigma equals 0, gives you a set of conditions for these functions omega, and you'll derive, you find that this first heavenly equation follows from there. And that is 4.2. Okay, so you can really, with some effort, close the loop and go between the Twistor formulation of Penrose and this heavenly formulation of Plebinsky, making the first one concrete and also providing some examples, new examples of solutions. So this formulation was later used to construct explicitly at the Twistor level all ALE instantons. See, out of these ALE instantons, the Gibbons-Hawking subclass corresponding to multi-centered harmonic functions with V0 equals 0, these were explicit. The other ones were not, but you can prove that at the Twistor level they are explicit. You can then ask what at the level of the Twistor space is special about the Gibbons-Hawking ansatz. So remember, Gibbons-Hawking ansatz is a subclass of all antiself dual Ricci flat solutions which admit this killing vector, which is triholomorphic. And what happens for Gibbons-Hawking is so what extra you need to assume about the Twistor space so that it leads to the Gibbons-Hawking ansatz? It turns out that this Twistor space has to admit a global, well, let me say it as a global function homogeneous of degree 2. by which I mean there is a global function on the Twistor space so that on each line it restricts to something homogeneous of degree 2. Let's say that this function is called Q, and what you then do with this function is you say I have this function Q, which I put in by hand, and I also have the symplectic form. Well, I can construct a Hamiltonian vector field for this symplectic form using this as a Hamiltonian. This gives you a global holomorphic vector field on the Twistor space. Well, that, so you look at the trajectories and they take points to points on the Twistor space, so they take alpha surfaces to alpha surfaces. So this in fact leads to a conformal killing vector. In fact, it is a killing vector in this case on M, and you can show that this killing vector has to be triholomorphic, so it boils down to Gibbons-Hawking. That's it. Right, so that's, so we've linked anti-self duality to Twistors via concrete examples and this construction. But there's something else I wanted to end up with, which is somewhat fresh, I mean, as in recent. And what would you want to end up with? Of course, the big gap in all this, as Roger has been pointing out for 40 years, is that this apparatus only applies to anti-self-dual spacetimes, and the real spacetimes like the Kerr solutions and others, they're not anti-self-dual and they're Lorentzian. So, is this physics? And it doesn't have to be for this to be interesting. I mean, it's very nice maths, and it gives you these instantones, and there are people who use this to calculate scattering amplitudes. Myself, I don't believe in these scattering amplitudes because they seem to be coefficients in the power series which is divergent, but there are great people who do great things with it. But one wants to realize it as physics. So Roger Penrose has posed it as what he calls the googly problem. He would want to encode the information about the self-dual part of the curvature in the Twistor space, and that's remained open despite many ideas. And I'm going to give you a modest resolution of this. So this is, okay, so what resolution will this be? You see, a lot of physics is actually non-relativistic. And there is, you can do a lot with GR, and there might be some lectures about it this afternoon, at the level where, speed of light tends to infinity. So Newtonian physics, and there is also Newtonian gravity. Well, you can ask, what is the Newtonian limit of Twistor theory? So Twistor theory is only anti-self-dual, but it turns out that its Newtonian limit, if you take it well, describes all Newtonian spacetimes in a kind of Twistorial sort of ways, which is non-local. So space-time points correspond to curves in Twistor space and whatnot. But you can really look at real physical Newtonian limits of spacetimes. So that's what I'll tell you about. And that's some work I've started some 6 years ago with my PhD student, James Gundry, then PhD student. And that's a paper in Communications Mathematical Physics, I think in 2016. And there is a paper which came out this year with Roger Penrose in Annals of Physics. And there is a preprint to which I'll give you a reference. Okay, so what this preprint does, and the first two works do not do, is the preprint takes the cosmological constant seriously, so allows it not to be zero. Okay, so the theme here is what happens to a Twistor correspondence in a limit when the speed of light tends to infinity. Okay, and so to understand, it might be that nothing happens, it all kind of dies. But to have a go at this question, you'll go back to this flat formulation of Twistor theory with alpha planes and not alpha surfaces, where everything is explicit, and you laboriously start, looking at the Lorentzian slice, you start introducing back the speed of light. So every time you saw t, you replace it by ct, and you take limits. And even that flat picture is interesting from the algebraic geometry point of view, because it corresponds towards an algebraic geometry called the jumping lines. Okay, so it might be too technical to be interesting, but I'll give it a go anyway. So what happens in this limit? And say answer jumping lines. So this, it goes back to this business about what is special about these CP1s in the Twistor space corresponding to points. And I said what's special is this type of a normal bundle. It has to be O1 plus O1. So you can think of a Twistor space as a total space. So let's say that you have a Twistor space, but now it's parameterized by C, because I put in the speed of light, and it's a Twistor space of flat Minkowski space, but with a given speed of light c. So it's a total space of O1 plus O1 vector bundle over CP1, and the patching matrix for this for this bundle is 1 lambda to the minus 2, and then I have, I think, C minus C lambda to the minus 1. 0. So this, you can really take it as a definition, and then you prove that it's equivalent to my previous definition. So you take a bundle over CP1, cover CP1 with two open sets, and take this patching matrix. Now, if C, so call it F, if C is finite, then you can write this F in the form H times 1 lambda to the minus 2, 0, 0 times H tilde inverse, where H and H tilde are respectively holomorphic in an open set where lambda equals 0, and holomorphic in an open set where lambda equals infinity. So you can factorize F like that. Sorry, it's not this. It's lambda inverse and lambda inverse if C is finite. And that tells you, I told you that the patching function for the line bundle ON is lambda to the minus n. So that tells you that this bundle is O1 plus O1. See, if C is infinity, then this dies, and your patching function is in the form which directly corresponds to a line bundle O plus O2. So, as a real manifold, you have not changed anything to the Twistor space, but at the holomorphic level, you've changed its holomorphic type. What you then find is that the way Penrose constructs and Twistor spaces, I was answering Abai's question the other day. I said there is something called Kodaira theory when you deform patching functions and preserve four-parameter family of curves. You find that this non-relativistic limit, so to say, is unstable under Kodaira deformation. So if you deform this, your lines will jump back into O1 plus O1. So that would mean that, I mean, physical phrase would be that the Newtonian physics is unstable under holomorphic deformations. I don't know what that means, but sounds catchy. I mean, when I gave these talks about it some years ago, it's quite true looking at the audience that nobody understood anything. But by the time I said this, that this is in holomorphic instability, people got, you know, overexcited and said it must mean something deep. Well, maybe it does. But more kind of hands-on calculation, because there is always a calculation at the end of everything, is what happens in the curved case. How do you get kind of non-flat Newtonian physics? And that will, so I'm going to go back to this Gibbons-Hawking ansatz and rewrite it slightly differently. So I'm going to consider a one-parameter family for a given function v, and this one form A. I'm going to construct a one-parameter family of Gibbons-Hawking metrics. So Gibbons-Hawking metrics, they were up there a while ago. They depended on one-harmonic functions. Okay, so it'll be 1 plus epsilon v kind of dx squared. That's the dx1, dx2, dx3 squared. Call this g epsilon. Plus 1 divided by epsilon, 1 plus epsilon v d tau plus epsilon to the power 3 over 2, you have to be careful with the epsilons, a squared. Okay, so you know it doesn't exactly look like a Gibbons-Hawking, but the point of putting these epsilons exactly as they are is that you can check that this metric is Ricci flat and anti-self-dual, so hyperkähler, for any value of epsilon as long as star dv equals dA, which in itself implies that v is harmonic on R3. Okay, now this epsilon I'd like to identify with 1 over speed of light squared. So why? I can hear you asking, I would want to identify it with 1 over speed of light squared. We have reasons for it, but which you can appreciate at the level of this equation. See, if I take v equals 0 and a equals 0, and that's a perfectly reasonable solution, then I have this 1 over epsilon here. Have I screwed up? No, actually I haven't. Good, I did mean this. You see, because this is that, because v is 0, and so is this, and I have d tau squared times 1 over epsilon. But if it was really a flat Minkowski space or its continuation, then the stuff which multiplies d tau squared would be c squared. So that's a good choice. So now you say, okay, this is Gibbons-Hawking. It has two things. It has, for any epsilon, it satisfies this equation. So there is a Twistor space, and it admits this global holomorphic function of weight 2, and it's fairly explicit. And there is this metric. So I can now try to take limits. Take a limit where epsilon goes to 0, or speed of light goes to infinity. Now, bad news is that in this limit, things are not looking good, because there is this 1 over epsilon which blows up. But it's okay, because in the Newtonian limit, the Minkowski metric or even the relativistic metric blows up. And there is no limit of this metric. So what can you do instead? Well, you can compute, and that's an exercise. You can compute the Christoffel symbols. Okay, so limit where epsilon goes to 0 of g epsilon doesn't exist. So compute the Christoffel symbols. See, and if you've computed Christoffel symbols, you remember the formula. So in the formula, there is a bit where is G inverse, and this G inverse multiplies lots of derivatives of G. So there is a chance, it's not a guarantee, but there is a chance that although the metric blows up in the limit, the connection doesn't. And that's what happens here. If you compute these Christoffel symbols, and you take the limit, epsilon goes to 0, you find that there is only one simple set of Christoffel symbols which doesn't vanish in that limit. And these are gamma, so normally you say Christoffel symbols of gamma A, B, C, right? And what stays in the limit is gamma tau I, no, nonsense, is gamma I tau tau, and that is a half delta ij dv by dxj. Okay, so you have a, I mean, more abstractly, in this limit you have a connection. It's an affine connection with no torsion, but this connection is not a metric connection. It's not straightforward to see. Well, it's not even metrizable, so it's not projectively equivalent to a connection with a metric. I mean, it's not entirely straightforward because there might be some other metric not arising as a limit of this metric which has this connection as a metric one, but it doesn't. It belongs to a class of Newton-Cartan connections. Okay, and right, and this, you know, if you're, I mean, in basic Newton-Cartan theory, this is all there is to it. So, I mean, in the Newtonian limit, the GR is, you know, you can think of motion of particles in GR as geodesics of this connection, and the Newton's equations tell you exactly that. So you can now interpret Newton's equations, which you write as x double dot equals minus gradient of, it's not quite this v, I need a factor of 2, so let me call it u, where u is Newtonian potential. You can associate a four-dimensional space-time with it, with coordinates x and t, n, and then the integral curves of n are geodesics of connection gamma I tau tau with v, with u equals 2v. See, one thing which happens is at the Newtonian level, there is, you might worry that we've started with a Riemannian signature, and where is, you know, we're taking this limit, but these are Riemannian solutions. How about Lorentzian solutions? Where at the level of Newtonian limit, there is no difference between time and imaginary time. It kind of decouples. So the bottom line is that the Newtonian physics or equations can still be described twistorially, where space-time points correspond to curves in a Twistor space, and these curves have a normal bundle O plus O2, and the correspondence remains non-local, so points in space-time correspond to curves in Twistor space. And that's, I think, just fine. I mean, theorems behind it. Now, some ideas in this paper, and to some extent this, is that, and these are, I must say, of speculations. So so there is this Twistor non-locality of Newtonian physics, and there is the quantum non-locality of the wave function. And Penrose's been of the opinion for many years, unlike many other physicists, that this quantum non-locality and the kind of reduction of the wave function is a real process which takes place in time. It's not instantaneous. So if it's a real process, it should be described by some sort of physics. And we make a proposal how the Twistor non-locality becomes at some level this quantum non-locality and can describe the collapse of the wave function. And there is a precise, the proposal might seem like out of the blue, and which to some extent it is, but there is a precise mathematical thing you would need to do to make it sound, and it's to do with real analyticity. The way the proposal works is we would like to apply these Kodaira deformation theorems where they're not normally allowed to be applied to kind of smooth category and not real analytics. So there's some work in progress, but it's interesting. So if I'll be looking at Twistor theory in the next 3-4 years, I think I'll be looking at this non-relativistic limit. So I propose to stop here, but now people were kind of approaching and asking me questions, and I'll be around this afternoon should you have any more questions. But I think there is nothing. Is there anything planned for the students? So I was going to say, if there is I stay near the Union Square. If there is a place for everybody to go for a drink, and I cannot say that all drinks are on me. Professor Lewandowski might say that, but I would offer drinks to the first 10 people. If we can find a place, if it's nice weather in the evening, we can sort of meet around and chat. I'll ask Adam who is here. No, he's not here. To find, so we thought about Plac Zbawiciela, right, as a possibility, but those of you who come from Warsaw might have better suggestions. But I'll stop here. Uh-huh.
I was speaking out of my desk, but I ran some abstract to the paper that there were experiments that were trying to falsify collapse models entirely. So they were doing this in some quantum optics circuits. Maybe somebody's so familiar with it, and they arrived at the null result that there's no collapse happening. So
I'm to some extent familiar. So when I started as a research student at Oxford in '96, there's a bloke called Dick Bovemister who started as a postdoc. And he, before coming to Oxford, he was a postdoc in Anton Zeilinger's group. Those of you who follow quantum optics world would know that Zeilinger got a Nobel Prize last year or this year. And so, but this was, as it happens with Nobel Prize, for the work done many years earlier. So I think this Mr. guy was influential. Anyway, and Roger was talking about this collapse, and Roger proposed an experiment to do with mirrors and putting a quantum state, a massive state, in a superposition with itself. And the proposal is that the time of the collapse of the wave function should, by sort of time energy uncertainty principle, depend on the mass. So the higher the mass, the quicker the collapse, which is why we don't see it with Schrödinger cats, but we do see superpositions in electrons. And so it's an experiment. And then Bovemister worked on this for 3 years as a postdoc, and then before he left Oxford for Santa Barbara, he said that we're 10 years away from this experiment because the technological barrier was big. And I see him every 3 or 4 years. We kind of became friends. And every time I see him, I saw him 2 years ago last time, he says, and he's got lots of money now, and these experimentalists, they could, one experiment budget they have would fund all of you for your lifetimes. But he still says we're 10 years away. So, I don't know, it might be in our lifetimes. It'd be very interesting if there are experiments which measure the time of collapse of the wave function as a real process. I don't know if it answers this question, but that's the kind
yeah, it always bugged me this trying to maybe experimentally verify collapse
Rod.
Just here with this, taking epsilon goes to 0. What about if you just stay in the world of projective geometry? Does the limit then? I know it's not then metrizable in the limit, but is the behavior sort of nice in the projective picture?
Well, I think it's okay. But I think the behavior is pretty nice in this picture because you do get this connection. I think what you're okay, you might be asking, I'm misunderstanding, but you might be asking the following question. For example, you might be asking, is there a metric, before you take the limit, which is projectively equivalent to this metric I wrote down here, so that if you take a limit where epsilon goes to 0, the metric survives? Is that the question?
Projective structure just smoothly goes to that limit, is what I meant.
Yeah, but but listen, but the projective structure does smoothly go to that limit. That's what we've shown. Because I picked a representative, which is a Levi-Civita connection, there's good connection, and it goes to this limit smoothly.
Right.
I think it's okay. Yes?
Yeah, relating like this local measurements and the with them, there's some research done by Twistor from University of York, and he actually argues that if we treat this measurement problem like rigorously using algebraic quantum field theory, then there is no problem at all. And that's, yeah, that's, as you said, that like the fact that there's some issues with this instantaneous measurements, this is a problem of quantum field theory, but it's not an actual issue that's like physical, and that there is no actual collapse. It's more, he thinks of it more like a state update.
I see. I don't know that stuff, but I know someone who is from University of York and does rigorous quantum field theory, and that's Kasia. We should invite Kasia, give us a talk about that. Maybe they collaborate. It sounds good. I didn't know about that. Yes.
Have people looked at the opposite limits, so like a C to 0?
Yeah, that's a very good. Yeah, in fact, they encouraged me to look at this. So there is this Crollian limit, which, I mean, at the face of it is just like not the limit you would want to take. So that's a limit where, if C goes to infinity, the light cones open up and become hyperplanes. If C goes to 0, the line cones shrink and become lines. But so this first came up in the work of Bakery and Lévy-Leblond on classification of kinematical Lie algebras, which is a fine thing to do. You can classify anything with any limits, but is there physics? But now people who do, so I don't know much about it, but people who understand, people who do BMS, they say that the way to look at this BMS group, and maybe Abhay will talk about this, is by this Crollian limit. So I've been nudged by people to look at the Crollian limit, but I haven't done it yet.
I know that there are some people who deal with Twistor theory in terms of wormhole geometry. Have you ever looked at that?
No.
Do you think that's possible? Or at least
I mean, do I think that it's possible that there are such people?
yeah,
The answer is yes, it's possible. I mean, is anything else possible beyond it? I don't know. Okay, that's it then.